The last talk in this session comes from Tanbir Haque. He's the principal engineer with the Technology Evolution and Prototyping Group at InterDigital Communications. Currently, he's leading efforts to research and develop various physical layer technologies for future 5G as well as 6G systems. His degrees he's received from New York University as well as Columbia University. So, Tanbir, please.
Thank you. Thank you. I'll talk about ultra-low power communications and air interfaces that are needed. I'll address some practical issues that need to be addressed in the near future. For the sake of time, I'll just simply state that going forward beyond 5G and into 6G, one key challenge that we'll need to address is how to deal with a trillion connected and sometimes moving things. Again, just for the sake of time, this is InterDigital's 6G vision. It includes things like terahertz radio, satellite communications, and etc. But I will focus on ultra-low power communications and air interfaces for ultra-low power communications. Looking into the challenges we face in scaling towards 1 trillion devices, the battery is the first natural place to start. As we've seen, and as many of you are familiar, battery energy densities haven't really quite kept pace with some of the other sectors in industry. For example, DRAM and even downlink air interface throughputs have increased several orders of magnitude, whereas the battery still remains a bottleneck. Just a simple exercise, if you consider 1 trillion devices with 10-year batteries, this results in 274 million battery changes per day. And increasing these numbers beyond 1 trillion, this becomes infeasible very quickly. And for some future deployments, battery swapping is simply not possible at all. So what is needed? We need to start thinking about implementing what are called forever batteries, and we'll explain a little bit what that means, and enable altogether battery-free operation of devices. Okay. A second challenge that's associated with sort of the 3GPP framework is latency versus battery life. As many of you know, a lot of the power-saving features in 3GPP, NR, etc., are duty cycling based, and we have these DRX and power save mode approaches that are all duty cycling based. But with these approaches, there is an inherent trade-off between device reachability and battery life. A longer DRX cycle results in extended battery life, but at the cost of latency. Furthermore, when the device enters power save mode, it is not reachable by the network. So what we need to do is to start to think about introducing on-demand features through the 3GPP system framework to break through this latency versus battery life trade-off. To get a better understanding of what this trade-off involves, we look at a power consumption profile of a device. What we show here is the relative power consumption of the device in various different modes as it goes through its life. The device may start with UL transmission, where it retransmits the same packet several times to close the link budget gap. Then it may enter its lowest power mode, power state, which is power save mode. And we note that in this mode, the device is simply not reachable by the network. So the device has to exit this mode periodically and make measurements to make sure that it is camped on the right cell, and it also has to periodically check to see if the network is paging it. And it'll do this, it'll continue to do this until a network event happens and it decodes a page and it realizes that it has to send an uplink packet, and it'll do so. The time period between successive uplink packets we'll call transaction cycle. With today's, so we take a quick look at what is possible with today's 3GPP, DRX, and PSM-based approaches. We consider a device that operates from 2 AA batteries, uses a power class 4 transmitter, and transmits an uplink packet that's 2 bytes. We set the DRX cycle to 20.48 seconds, and we explore the battery life as a function of transaction cycle for various different measurement cycles. And we see that for a measurement cycle and DRX cycle of roughly 20 seconds, a battery life of roughly 6 years is possible with a transaction cycle of 1 day, and roughly 8 years is possible with a transaction cycle of 5 days. One might be tempted to say, why not just increase the DRX period? The problem with that is, as you do that, the time required for synchronization grows quickly, and you find out that it's a diminishing return. So what is needed and how do we get there? There's 3 elements, we believe: ultra-low power radio receivers capable of supporting macro-like link budgets, what we're calling a zero-energy air interface that does not draw power from the device's battery, and of course a scalable system framework that can support diverse deployments. First, we look at a quick survey of ultra-low power receivers that have been published to date. We show two plots. On the left side, the graph is separated in terms of frequency of operation, and on the right side, it's separated in terms of whether it's capable of coherent reception or not. And we define ultra-low power as receivers that consume less than 1 microwatt of power. And we see that devices that are ultra-low power by this definition and are capable of, let's say, close to minus 80 dBm sensitivity, they're inevitably operating at sub-1 gigahertz frequencies. They're non-coherent, meaning envelope detection-based, and they use simple modulation schemes. So we need to reckon with this. We need to deal with this. So what we did was we modeled one such direct envelope detection ultra-low power receiver, and we basically created an extensive behavioral model, and we plugged it into our 3GPP NR link level simulator, and we observed the results that we got. We used, as I mentioned, Manchester encoded on-off keying signals. We used NR-RE level tones to construct the underlying waveform, meaning 15 kilohertz tone. We used up to 4 of these 15 kilohertz tones. We used gold sequences to construct the unicast wake-up signal, and we explored effective data rates ranging from 200 bits per second to roughly a few kilobits per second. And we observed that, and we used the probability of misdetection as a key performance indicator, and we observed that in an AWGN channel, the required SNR for this level of probability of misdetection ranges from 1 to 3 dB. And we also note that as you introduce a fading channel or in-band blockers, these curves tend to shift to the right. So what we conclude is that a 140 dB free space path loss at 900 megahertz can be supported with a 1 kilobit per second ULP receiver that consumes less than 20 nanowatt. So let's see what we can do with this. So then we start to explore what we call zero energy air interfaces, and let's go through what we mean by that. So the receiver here, it might be an ultra-low power receiver, and it may be capable of both harvesting and decoding wake-up commands. The receiver will likely have, in this sort of arrangement, 3 states in its states machine. It'll have a harvesting state, a training state, and a decoding state. And the commensurate signal that the network will have to send out to make sure that the receiver harvests enough energy before it enters the training and decoding phases, such that it doesn't have to draw energy from the battery. So the signal will consist of a preamble, and then the body will consist of, as I said, a training sequence and a decoding sequence. And the whole idea is that you create a large enough energy surplus during the harvesting state such that the latter 2 states don't have to draw any energy from the battery. And so one natural question becomes, well, how long do these preambles need to be? We explore that a little bit next. Here we consider a very simple example where we take an antenna and split the power. send part of the power or most of the power to a power harvester, and the rest of the power to an information receiver, such as a direct envelope detection information receiver. The whole idea is that the power harvester stores the harvested energy during the preamble in a temporary storage of some sort, or perhaps a rechargeable battery, and that surplus energy is used by the information receiver to decode the remaining part of the wake-up signal. And the idea is that this harvested energy minus the energy consumed by the receiver to do the training and decoding has to be greater than 0. And using sort of a 6 dB coupler, we find that we wanted to see, well, what is really possible? What is supportable with a let's say 10 nanowatt receiver and a 1 second preamble? We find that roughly 128 dB path loss is supportable. And of course, if we wanted to support much higher path losses, the preamble would grow. So now we take all of this and sort of put it into a system framework. And of course, we conceptualize that we would do this in 3 stages. Initially, our goal is to just increase the battery life of existing NB-IoT devices, and going forward in the intermediate and long term, we would enable forever batteries. Forever batteries meaning batteries that last the lifetime of the device, and in the long term altogether, do away with battery and enable battery-free operation. So to do this, let's start with the NB-IoT scenario, where let's say we have two devices that are capable of using the UU interface to access, receive, and transmit data. They're capable of DRX and power save modes. First thing we do is we introduce a zero energy downlink, a companion downlink to one such device, and we introduce on-demand wake-up signals to the network. These wake-up signals would consist of a preamble and training and decoding sequence, as we called it. And this is the scenario that we'll explore a bit in detail. And of course, in the longer term, we can do away with the UU interface for certain scenarios and just simply have a zero energy uplink and downlink, where we would send on-demand wake-up signals in addition to controlled wireless power. So how do we introduce on-demand features to the 3GPP system? We consider several different parts. One is, as I said, introduce these zero-energy companion interfaces. Of course, introduce on-demand wake-up signals that deliver power and information over the air. The next few are very important. We ponder moving mobility management related RSSI measurements to the zero energy air interface. And we also consider dynamically controlling the NB-IoT uplink transmission repetition behavior with the zero energy air interface, and I'll explain what that meant. And we can also consider transferring wireless power to these devices to compensate for example, idle mode leakage power. And so we just quickly walk through this and see how this might work. Again, the device would start with an uplink transmission. Maybe you'd have to repeat the same packet several times, and it would basically enter sleep mode, and it wouldn't wake up periodically. There would be some sort of network event. The network would send out an appropriately sized preamble and an actual, perhaps unicast wake-up signal. If the device is able to harvest enough energy and successfully decode the wake-up signal, it would wake up, use the UU interface, and find out that it's being paged, and it would start the uplink transmission. It would repeat packet transmission to overcome path loss. The network might successfully decode the message before the pre-configured number of UL transmissions are required in the network. Within that point, send a wake-up command to stop transmissions. Now, with this, what can we achieve? So here again, we show the battery life in terms of years as a function of transaction cycle, and the black curve is really what we're going after. It's where we put everything we've talked about all together. Again, the same sort of scenario: 2 AA batteries, 2 bytes of uplink, and power class 4 transmitter. We see that if we pull everything together, we can hope to achieve roughly 22 years of battery life for a transaction cycle of 1 day, and more than 40 years of battery life for a transaction cycle of 5 days. So some final thoughts I'll leave you with. So basically, we believe that scaling to 1 trillion devices will require us to reimagine the radio transceiver, the air interface, and the overall system. We will need to break through the battery life versus latency trade-off that exists in today's 3GPP duty cycling-based approaches. We will have to develop ultra-low power receivers that consume tens of nanowatts of power and are capable of macro-like link budgets. And then, of course, we'll have to introduce these on-demand features to a 3GPP NR-like system. Thank you. Thank you for your attention.
Okay, Tanbir,
Thank
you
you.
very much for
Thank
the
you.
interesting talk.
Thank you.
Any questions from the audience? There.
Hello, Ben from Samsung. One of the elements that consumes a lot of power in the radios is the front ends that have to be quite linear because we operate in a multi-operator model. So you get 2 base stations, and so the blocking specs tend to be quite high. How does your system work with very high levels of blocking?
Now, high levels of blocking in terms of the zero energy air interface or in terms of the UU interface? Okay, well you know, we don't really introduce anything new to the UU interface. So whatever methods are there for dealing with high levels of blocker, the UU radio remains unchanged. We basically introduce a companion low power radio. So as far as methods that exist today to deal with high power blockers, that is, you know, we don't address that. Yeah.
Any other questions? I have a practical question.
Yeah.
How to test 22-year battery life?
We didn't test it. We modeled it. Yes. That's the easy answer. Yes. Yes. Yes.
Yeah, I figured it's going to be a difficult
Yeah.
test.
It was strictly modeling.
Yeah.
Yes.
Excellent. Thank you very much.
Thank you.